And at the beginning, I would like to just make a short introduction into lipids, just to remind you what you remember from high school, and then I will go to more depth. So phospholipids, the most common type of lipids in nature, I guess, or certainly in living organisms, have three main parts, or which are the head, the sort of connecting linker, which in phospholipids is glycerol phosphate, and then there are tails. And the most important property of lipids, or phospholipids, phospholipids or lipids in general, is that these parts have different relationship with water. So the heads and the linkers are hydrophilic, whereas the tails are hydrophobic. So each time there are more lipid molecules that are trying to stack together in some way, these hydrophobic interactions play a role. And of course, the hydrophobic parts stack together and the hydrophilic parts end up pointing towards the solution, towards water. So to look at cell lipids in more depth, these are the main types of lipids that are present in the cell. Sorry, can you see my mouse?
Yes.
Awesome, thank you. So the PC head group phosphatidylcholine are the most common lipids. They are uncharged and they have the phosphatidylcholine head. Then other common groups are ethanolamines and serines, out of which the serines are negatively charged, which together with phosphatidylinositols, which are also negatively charged, plays a major role in signaling. Then there are sphingomyelins. These are lipids that instead of having glycerol phosphate connection, they have sphingosine, which is crucial in because it has this double bond which makes the lipid stiffer. So it plays a crucial role in stiffening the membranes. And then they are also glycolipids, which also play a role in the signaling outside of the cell and in immune systems. In each case, there is a sugar moiety. The sugar moiety can also be phosphorylated. So if you ever seen PIP lipids, these lipids are very crucial in the various signaling pathways, and they have or they change their reactivity by phosphorylation. And when we have a look at the tails, so these are the 5 major tails that are present in the body. So you have palmitoic acid, which is straight and it's unsaturated. So it points down straight. In contrast to oleic tail, which has this double bond, which allows it to or makes it to point to the side. And then there are polyunsaturated chains like arachidonic acid or DHA. And if you ever seen some advertisement for omega-3 and omega-6 fatty acids, so there's these 2 guys. So this is something that you possibly saw somewhere mentioned that plays a role in the health of the human body. What also plays a role in health is cholesterol. And cholesterol has basically the same role in cell membranes as it has in the arteries. So the advice is that you shouldn't eat too much cholesterol because it stiffens your veins. Cholesterol also stiffens membranes on the cellular level, but actually it's crucial for their function, at least in normal common sense amount. So where are lipids in the cell? So the short answer is everywhere. Starting from the cell membrane that kind of holds the whole cell together. Then the membrane around nucleus, endoplasmic reticle, Golgi apparatus, or the small compartments that manufacture and sort proteins. In mitochondria, the inner structure where there is the charge gradient that generates energy or helps to generate energy, there's also lipid bilayers. And also lipid vesicles, these sort of small packages of compartments surrounded by lipids, either endosome, exosomes, vesicles, or lysosomes, are basically the main way how the cell can exchange everything with its environment. So if the cell needs to send something outside, for example, if you have nerve cells that want to move the charge or the signal from one cell to another, they do it in a way that they release neurotransmitters into the intercellular medium, and that's done via endosomes. On the other hand, if the cell wants to take in something from outside, it's usually through exocytosis, endosome, and lysosomes. So lipids are very crucial in any part of the cell that there is some sort of compartment, including the outer cell wall as well. And because these different compartments have different properties, what the cell does is that it makes use of this wide variety of lipid of the combination of head groups and tail groups. So the various membranes can be differently charged. They have charge asymmetry, which is done basically by head group asymmetry, but also uncharged head groups can also differ in their localization. There can be a difference in unsaturation. So unsaturated tails are usually longer and less ordered, while the other way around. Saturated tails are straighter and more stretched and more ordered, where unsaturated tails point to the side, so they are more fluid. There can be domains based on that. And the membrane can also be curved based on the combination of lipids in each leaflet. And all of that is also related to proteins. So in the plasma membrane, it's said that about half of the mass of the plasma membrane is proteins. So the proteins both react to the composition of the membrane and sometimes can also induce changes like curvature or some thickness related things. So to have a look how this great variability of lipids in living cells looks in the real life, there is this recent study that looked at the plasma membrane, so the outer membrane of the cell of red blood cells, because red blood cells are reasonably easy to get and work with, even from humans, so you can get volunteers to give you blood cells. And what they did is they found out that there are about 400 unique phospholipid species. So there's 400 different combinations of head groups and tail groups. And in the outer plasma membrane, there is a large asymmetry between the leaflets. So the exoplasmic leaflet, the leaflet that points outside of the cell, there is a large amount of PC lipids with different unsaturation. There is lots of sphingomyelins, and the unsaturations are not that high. So the most is like 0 or 1. So the outer leaflet is uncharged, and there is all the components that make the membrane stiffer. Whereas in the cytoplasmic leaflet, the leaflet that points inside of the cell, we can see that there is almost no sphingomyelin. There is the charged PS lipids, PE lipids, and also some PC lipids. But what you can see is there is more unsaturation. So there is the 4 unsaturations. This is the omega-6 fatty acids. There is the 6 unsaturation, which is the omega-3 fatty acids. So as you can see, the plasma membrane, the outer layer of the cell, really has these fine-tuned properties that is stiffer on the outside, more fluid on the inside, and that is achieved by this wide range of lipid species that are involved in each of the leaflets. So how can we simulate something like that? So the easiest, most commonly used way how to simulate lipid membranes is by a bilayer. So usually the bilayers are built in like geometric ways. You just have a grid and put the lipids there and then just let it run through equilibration process. But also what you need to take into account is like how large your membrane is, especially because you don't only simulate the membrane, right? You also simulate the water above the membrane. So if you increase the area of your membrane patch, then the water increases as well. The number of water molecules increases as well. So that's something that you need to keep in mind. So that's why a usual simulation has only like 100 to 300 lipids molecules in a leaflet. So you can clearly see that it's impossible to simulate 400 lipid molecule species. And as a side note, all the simulations of membranes are pretty crowded, so you usually cannot see very much. So the usual thing we do is we just hide the water, hide the ions, hide everything, and just show usually the phosphate atoms or nitrogen. So if you see a picture of a membrane that only shows part of it, there's always the water and the rest of the molecules. We just hide them so that you can actually see something. So what do we need to take into account when we are building a molecular simulation of a bilayer? So the first thing is to decide if you want to do an atomistic simulation or coarse-grained simulation. So having a look at a resolution that is connected to the problem you want to study. And then in this case, I will focus on the atomistic simulations because that's what I'm more familiar with. And the next step you need to take into account is the force fields. So there were great talks about force fields yesterday. So just to add into that, the two main force fields for lipids are amber and charm. The thing with amber is that it has somewhat limited a number of lipids that are available. On the other hand, charm have so many lipids, so many combinations, and that you actually have to think about like how many lipids you actually need in your system because there's so much to choose from. And also, if you ever find yourself trying to simulate some lipid-based system and you don't know where to start with the force field, our group made this review of ways how to simulate lipid-mediated anything or lipid-based anything. So I actually did this part of the table. It took me about a day because there are so many different ways of the OPLS lipid force fields, and it took me a while to make my way through all the different versions because I don't usually use them. But so they are now in the review. Anyone can read that. So if you ever need to use some sort of lipid anything and you don't know where to start with the force field or the process, I just want to direct you to this review. Another thing you have to think about when building a lipid systems and choosing a force field is that if you have a more complex systems, for example, with a membrane protein, some nucleic acids or materials, you have to keep in mind force field compatibility. So one of the reasons I have seen people use the OPLS force field is because they wanted to add some material and they found it easier for them to use that. So in this case, there is graphene nanomaterial with silver. So that's something that limits your choice of your force field because you cannot combine anything with anything and get reasonable results. And finally, a sort of side note to this matter of building a bilayer systems. So it kind of depends also, like the tool you use to build a bilayer depends also on like what else you would like to add into the systems. So if you would just want a bilayer, that's like pretty straightforward. But if you want some proteins, some material, or something else, it's different tools needs different inputs. So it's also good to think about it before you start. So yet again, this computational methods review and also this we kind of touched it for more complex systems in the perspective and the cozy small structure special issues. So if you would like to know more and read something about it, I'm just happy to direct you to that. And with bilayers, I would like to introduce the first 2 or 3 phases that lipids take. And also I would like to, so the 3 main phases are that are found in the bilayers are called liquid ordered, liquid disordered, and shell phase. And I know we discussed it at the general meeting because for people that come from physics background, it's really hard to imagine liquid phases. So I would like to imagine butter. And we are currently in the middle of a heat wave. So if you put your butter outside, you will get liquid butter, melted butter, which is actually a real life liquid. You can, it's a liquid, right? You can drink it. You shouldn't, but you can. On the other hand, if you put butter in like normal room temperature, it is soft. It's not quite liquid, right? It's not a fluid, but also it still holds together, right? So it has some sort of structure. It has some resistance to, if you try to put a finger into it, it kind of resists a little bit. So that's a way how you can imagine liquid disordered phase. So it's kind of soft and it's sort of liquid, but it has some sort of internal structure. It a little bit. It holds together. If you put your butter in the fridge, you get something that is sort of analogous to the liquid ordered phase. So the butter is stiffer, and the butter is, it resists being cut into pieces a little bit. It's not a crystal. It's not like a solid object, but it's you can see the difference if you move your butter between fridge and your kitchen, you can see the difference in the properties, right? And the shell phase is like if you put your butter in the freezer, it's kind of prone to breaking. It splits along planes, but it's not actually like solid, crystal anything. So these are the liquid order and liquid disorder are 2 main phases that are present in the living membranes. So I'm gonna talk about them a little more. And these 2 phases and their presence and interactions is really important for the cell, especially when it comes to proteins, right? A lot of proteins, a lot of membrane proteins kind of anchor into the rafts, or on the other hand, they can preferentially localize in the disordered phase, or they can move between the phases. So on the picture here, you can see that the lipids, the lipid ordered phase is stained by green, and the protein is stained by red. So in this picture, you can see some overlap, but they are not like 1-to-1 completely there. But in this picture, it's very, very clear. All the cells are orange, so the green of the rafts or the ordered phase and the red of the lipid of the proteins are in the same spot. So I will stay with this TLR protein for a little bit because, as I said earlier, there's 400 lipids in the outer cell membranes, in the plasma membrane, the outer membrane on the outside of the cell. And we have been trying to think about like how to build a model, right? Which lipids to include, which lipids not to include. So what is like the complexity necessary and simplicity available? So we decided to use this TLR protein, which is known to be associated with rafts, and it has they play some role in the reaction cascades because they are proteins of the immune system. And we choose to focus on this transmembrane region, this tiny helix that is in the transmembrane region of the protein. And what we did is that we built 7 different membranes. So on the top here, we have 3 membranes that are trying to mimic the plasma membrane of a cell. They are different approximation, different with different number of lipids. So you can see we get as high as 18 lipid species in the system, which is, for me, I guess it's like the edge of reasonable statistics, because then that's something you can still, sort of sort. So these are the 3 membranes. They are asymmetric, and they are built. They have been mentioned previously in different studies, and they are trying to mimic the plasma membrane. Then we have 3 simple lipids of POPC and cholesterol, and POPC, cholesterol, and sphingomyelin. They are trying to approach the problem from the other side and trying to figure out, okay, how simple can we get? The POPC membrane is often used in membrane protein studies, so that's what people would embed protein into. So that we started it, and we just added cholesterol and sphingomyelin, because sphingomyelin, as we saw, is an important component of the outer leaflet of the plasma membrane. And then we have this small membrane that was used experimentally to actually capture the structure of the protein. So when we look at the basic results and the basic properties of the membranes, we can see that actually the asymmetric membranes are pretty similar in their mass density. But what we can see very clearly is the asymmetry in charge. So you can see that the inner leaflet, the leaflet with the PS lipids and the PI lipids that have the negative charge, really, makes the inner leaflet very negative in the charge distribution, or missing the positive peak of the charge distribution. But otherwise, the membranes look like pretty similar from this point of view. In the simple symmetrical membranes, there are some differences. But yeah, we can see that the charge is symmetrical, right? Because it's a symmetric membrane. So to highlight the trends that we can see, I chose to depict it in the way of membrane thickness. So membrane thickness corresponds a little to membrane ordering in the inverse form. And what we can clearly see from this property is that there is a group of membranes that are actually very similar in their thickness in this property. They are actually within the standard deviation of each other, so they are actually statistically same. And then we have 2 membranes that have a different properties, different thickness. So the difference between the membranes is that all of these membranes that are in blue contain cholesterol, and these 2 don't. So what we actually see in this graph, and we can see it in other analysis, I just chose to show membrane thickness because that's the clearest way how to show that. What we can see here is the difference between liquid ordered and liquid disordered phase, right? In the presence of cholesterol, which is depicted as this like tails here, the membrane is thicker, it's more ordered, and in the absence of cholesterol, the membrane is thinner, it's more disordered. Now, if we put a protein in there and we ran 5 replicas of each membrane for 1 microsecond, so there has been a lot of sampling, and basically the main difference is the same as with the membrane properties. So in the liquid ordered phase, the protein stays more or less in this hockey stick conformation, which is similar to the starting structure, and it doesn't fluctuate very much, or there are no like dramatic changes in except for something that is topic for another presentation. But yeah, it makes it most of the time across the 5 replicas of each simulation of each membrane, it still stays in this form. On the other hand, if we have the liquid disordered membranes, the protein is more tilted, more unwound. We see some changes, and the whole thing is more dynamic. especially across the 5 replicas. So this is so this is just the way to show that like the membrane phase, even in the bilayers, when basically the only phase there is ordered or disordered, that the phase really plays a role in how the membranes react and how the proteins behave in the membrane. So bilayers are great, right? There are people that spend their whole life just studying bilayers and systems with bilayers and membrane proteins, and they are useful for many things. It's a good approximation. It can be used to study permeation, interaction with materials, interactions with protein behavior, so many ways of protein behavior. But when we look at the real life situation, we can see that there are like a lot of complex 3D structures, even when we're looking at a cell. So to move from bilayers to the 3D, we need to first go back to the basic structure of the lipid. So in the bilayers, the lipids that are mostly there, or the majority of lipids that build bilayers are these ones, the ones that have all more or less same area of the head group, of the tails. So they are this cylindrical shape. But you can also have the case where your head groups is slightly bigger than the tails. Or you have the case where the head group is smaller relative to the tails. And yeah, we have already seen the stacking into the bilayer. And if we have a larger head and smaller tails, the system curves in a way that the head groups are on the outside and the tails are pointing like inside of this bubble. And when you have a smaller head and larger tails, or like wider tails, you have a curvature that bends in the opposite direction, basically. So this can be described mathematically using a packing factor. And the packing factor basically takes the real volume of the molecule and divides it by simplified approximation using approximation of the volume using the area of the head group and the length of the tail. So this graph basically shows the same thing I showed in the previous slide. So if the head group is larger, then or if the ratio is smaller, then we get like spherical structures. If there's more or less 1, we get lamellar or bilayer. And if the ratio is higher than 1, then we have tails that are kind of large. That's when it gets very much fun. But before we get to these inverse structures, I would like to take a short break and just talk about some sea organisms. So this is a really nice study in the Journal of Science that I think really illustrates the great diversity of lipids and how crucial they are to life. So basically what they took was I think 6 species of different jellyfish, comb jellies, that live in the different depths of the ocean. And they analyzed the composition of their membranes. And what they found that, each jellyfish is well adapted to the pressure range they live in, right? So, and yeah, you need for an organism to have a functioning liposome, you need membranes that are liquids. They have combination of liquid ordered and liquid disordered patches, but also they have the ability to curve, right? Because you need curves in organelles, or if you want to start a cell division or something. So you also need the ability to curve the membrane sometimes. So what they saw is that when they took the membrane of shallow water jellyfish and put it under pressure, the membrane stiffened and basically moved into the gel phase, and you cannot do anything with the gel phase. On the other hand, when they took the deep sea jellyfish membrane and put it into normal pressure, the lipids or the membrane started curving and basically fell apart, which is also like one reason that that's why, you know, all the deep sea organisms look so terrible on the pictures that are taken on the boats, because they are adapted to very, very high pressures and they just start falling apart when they are removed from the pressure. So I just want to like take a short moment to just point out that basically every time there is an organism that lives in any sort of extreme environment, they have lipids in their membranes, and the lipid composition is also evolved to handle this really wide range of extreme environments to keep the cell together, you know, be it jellyfish or you know, fish or bacteria that lives anywhere they want. So with that, let's go back to theory. And I would like to talk a bit about the theory of curvature of the lipid membranes. And from now on, I will only talk about the inverse structures. And I will probably forget to say the word inverse, because that's especially in the hexagonal phase. So it's inverted hexagonal phase, but no one actually says that because the non-inverse hexagonal phase happens so rarely. But this is what we are talking about from now on. So to have some theory behind this, the theory is it's like pretty simple. So you have a curved monolayer, single layer, that has two principal curvatures, which are defined as the radius of the curvature in the two principal axes. Then the mean and Gaussian curvatures are then defined either as the mean or, you know, as the sum, not sum, multiplication of these two principal curvature. And the real fun happens when you have two monolayers, right? So you have two monolayers that have different curvatures, then they can meet. That can be done by the lipid composition of the membrane. And then depending on the combination of the curvatures of these two monolayers that make a bilayer or that meet together, you can have this like really huge variety of shapes that are really complex, but can be described using, you know, geometry or simple geometry, or it's basically simple geometry behind it. So to illustrate that a little more clearly, these are the inverse phases that actually that have been described theoretically, that have been observed in the real life, as you can see. So starting from the normal bilayer, multilayer lemma phase, we can get to sponge phase. There are these free PN-free, EM-free, and FD-free M phases that actually can move between each other. They are based on the minimal surfaces, and they are really very complex. This is one of the like clearest depiction of what they actually look like. We have the hexagonal, inverse hexagonal phase, or you have just like fluid isotropic phase with just bubbles of the solvent. And the thing that decides which of these phases a lipid mixture is going to assemble into depends on the composition of the lipids, because usually, it's composition of the lipid mixtures, because usually we don't only have one lipid. So it's kind of a sum of the properties of the lipids in the mixture. It's dependent on temperature, and it depends on pressure, as we saw in the case of the jellyfish. And also it depends on like how much water there is available to the system. A group of lipids that are famous or, you know, infamous for their unusual properties are ionizable lipids. So ionizable lipids are a group of chemically manufactured lipids. So they have been designed to mimic, you know, the lipid composition of having head groups, tail groups, and connected by a linker. And in contrast to normal phospholipids, ionizable lipids usually have a relatively smaller head and relatively wide tails. So you can see there in these batch of tails, there are two unsaturations, which makes the tail bend outwards. In this case, there is a branching, which also gives the tail more flexibility, or a combination of heterogroups that kind of allows the tail to go wider. So the preferred shape of these ionizable lipids is this small head, wider tails situation. But in addition to that, they also have these ionizable nitrogen groups. So the nitrogens can change their charge depending on the environment, right? And these lipids are engineered in a way that actually the nitrogen can change their charge around the pH 6 to 7. So that's why they can be used in the normal body pH. And the thing with the charge and the lack of charge, or the ability to change, is that it touches the basic property of a lipid molecule, which is the amphiphilicity, that it has hydrophilic head groups and hydrophobic tail groups, right? So if you have a nitrogen that can change the charge, that also plays with this relationship of the molecule with water, or the bulk solution. And the reason everyone is talking about ionizable lipids in my corner of the world is because they can be used in medicine, and they have been used in medicine. So the property that it changes the charge is very useful during the process of endocytosis, when something is taken up by the cell. And in the process of endosome maturation, the pH changes in the endosome. So this is something that the ionizable lipids take advantage of, in this process. And because of the lipids are so specific, the inner structure of nanoparticles is also complex compared to like lipos and vesicles, which is also used for some drug delivery. And the most famously, lipid nanoparticles have been used in COVID vaccines. So there have been Pfizer and Moderna mRNA vaccines, and both of these mRNAs are wrapped in a lipid nanoparticle with ionizable lipids. But also, lipid nanoparticles also have been used for this rare disease medication where they also deliver RNA. So if you look inside of the lipid nanoparticle in this schematic view, there are multiple components. So the first thing is the cargo, which is RNA. Then there are the ionizable lipids, about half of the composition. There is cholesterol. And when I first read the composition of ionizable lipid nanoparticles, I was really surprised because there's such a high amount of cholesterol compared to like normal cells. Because if you have a normal phospholipid bilayer and you have like 30% of cholesterol in there, it's already pretty in the pretty firmly or in the liquid ordered phase. But here there's almost like 40% of cholesterol in some cases. So there are a lot comparatively. There is some helper phospholipid, usually the SPC or the OPE. And then there is this pegylated lipid that is thought to coat the lipid nanoparticle from the outside. It has this very, very long polyethylene glycol unit chain. So these 36 units really go all the way up somewhere. So they are usually on the outside of the lipid nanoparticle. The nanoparticle has complex internal structure. The inverted hexagonal phase is the one that is most commonly discussed in this case. There is some separation between layers. I think the hypothesis is that the helper lipids are somewhat more frequently located on the surface has been also confirmed pretty solidly recently, but we'll see later. Yeah, and the size of the lipid nanoparticle is in the like tens to slightly over 100 nanometers. So it's still nano, but it's too big for us to simulate a molecular dynamics simulation realistically. Here I would like to make a short note about the RNA and why RNA needs such a complicated systems to be carried by. So organisms usually don't, RNA is used in the cell for transcription and of proteins. So the cell has really a lot of housekeeping proteins, housekeeping cascades that make sure that RNA only does what it's supposed to be doing, right? On the other hand, when you add RNA to a cell, it can serve as a template or in the like RNA interference way. So we can actually, if you manage to get RNA into a cell, you can make the cell to do things for you, which is very useful. But RNA also has like very, very complex internal structure, right? We have seen talks earlier about DNA, and DNA usually stays in this double helix that is reasonably stable. However, RNA can do all sorts of loops, hairpins, junctions. It needs ions to stabilize some of these junctions or complexes. So the inner structure of RNA is really, complicated, and it's a molecule that reacts easily. So that's why we are trying to wrap it up in the lipid nanoparticle to deliver it where we need it to go. And one thing that the ionizable lipids help to protect the RNA is when they are charged, they are in the protonated form, there is a positive charge on the nitrogen atom, right? And as you know, or as you can extrapolate from the DNA talk earlier today, there's a lot of phosphates in the backbone, and the phosphates also need counter ions. So, I mean, they are, normal ions. We usually potassium in our simulations, but also the ionizable lipids and their positively charged nitrogens can serve as a counter ion to counter the negatively charged of the phosphate backbone of the RNA. On the other hand, when they are uncharged, they lose this ability, and then sometimes there are the helper lipids that can help stabilize the RNA, or the RNA is not very happy in the uncharged form of the when the lipids are in the uncharged form. So in this picture, I just wanted to illustrate that while there is a lot of the hypothesis that there is a hexagonal phase inside of the lipid nanoparticles, in reality, it's very hard to check. Because as you can see in this cryo-EM images from 2021, the resolution is not quite there yet, and there is, I mean, we can see there is like complex internal structure that sometimes it's just spherical. The lipids and RNA are mixed. Sometimes there is these bleb forms which are supposed to be RNA here and lipids here, but it's really hard to like have some like detailed understanding of what's going on inside. So that's why we decided to simulate the vaccine or vaccine mixtures and try to see how they behaved. So even though these are very unusual lipids, we did the thing that lipid people do every time, and we defaulted to the bilayer. So we built a bilayer of this ionizable lipid that is present in the Pfizer vaccine. It's on the left here, on the right here. So what we can see that in the charged form, in the protonated form, it holds the bilayer. it's a thin bilayer. It's a very, very disordered bilayer, but it is still, somewhat in a bilayer shape. On the other hand, if the lipid is deprotonated, it loses its charge. The membrane or the bilayer kind of condenses into like this liquid droplet and loses all the internal structure. So what we can see is there actually another effect of the charge, and that is it makes the effective size of the head group slightly larger, so that in the charge form, in the protonated form, the lipids can still, have a similar situations or similar behavior to lipids with comparatively larger head groups. But when the head group is deprotonated, it's neutral. Then everything just mixes together into this oil droplet. When we try to do it with the whole mixture of the ionizable lipids that are in the nanoparticles, so we have all the four components, we can see that this is not pre-built, this is self-assembled. So if we don't have, we actually see a pretty large effect of water. So if we have a small amount of water, the system assembles into a bilayer. But if we increase the water content more and more, we can see that the bilayer kind of gets perforated. There are holes, or they kind of connect through the periodic boundary condition into this cubic phase. And sometimes when there's a lot of water, we can actually see the nanodisk, like this nanodisk forming. And we actually made use of these nanodisks and prepared them separately for a different study. So when I talked earlier about how sometimes there is a separation of the helper lipid and ionizable lipids, and you can clearly see it in the charged nanodroplet here, because in the middle there is this separated layer of cholesterol in yellow and the helper lipid in gray and orange. And it's really like small flat nanodisk. On the other hand, if we have a look at the deprotonated neutral uncharged form, the lipids are more mixed, but also the nanodroplet is like more spherical. It's more rounded in shape. And they are really like tiny nanodroplets of 100 molecules. And we prepare them to study this part of the process of the life cycle of lipid nanoparticle, because there are many hypotheses about how it actually gets outside of the endosome, or how it releases the cargo into the cytoplasm. And one of the hypotheses is that it merges with the membrane of the endosome. So we're like, okay, let's try that. Let's try to merge them and see what happens. So we prepare these systems of the ionizable lipid droplet and membranes with different head groups. And in the charged form, basically every time this is what happens. So the ionizable droplets stays connected to the outer layer of the leaflet. There is exchange of lipids, and it's like stable across like hundreds of nanoseconds of the simulation. On the other hand, if we have a look at a deprotonated case, the lipid droplet actually dissolves into the membrane. The uncharged ionizable lipid can flip-flop across the membrane center. They can go to the lower leaflet. Sometimes they bring cholesterol with them, but the membrane is pretty well mixed. One case when this process happens, in 3 replicas of these 4 systems, but one case that was specific was the system with the PE head group. So if you remember, as I said earlier, that the PE head group is actually the smallest of the head groups of the lipids that are commonly found in nature. That also is manifested in the fact that it has this tendency to curve and create curved layers. So what we can see, what we could see in these simulations, that then again it was 3 replicas, so it's pretty, statistically it has been shown. It happened multiple times that in the 1 microsecond in which all of the other systems were already, dissolved, there was still this like droplet of ionizable lipids that's in the deprotonated form that stayed inside the bilayer of POPE lipid and actually needed some extra couple hundred nanoseconds that stay there to like dissolve completely in the bilayer. So that's something that was actually pretty interesting to see, and that actually shows us how the ionizable lipids and normal cell membrane lipids can interact. The membranes were a little modified, but actually the merging did not change the properties dramatically, so the membranes didn't fall apart or anything. And I would just like to point out in this graph, in this image, how the 2 or 4 tails of the ionizable lipids are very flexible, because the normal POPC lipid just can stretch the 2 legs, the 2 tails it has only so far, but the conformational flexibility of the ionizable lipids, it's so wild. We also had a look at the lipid nanodroplets on larger scales. So actually call these nanoparticles. I think there are 4,000 lipids, if I'm not wrong. And what we could see is that in the presence of RNA fragments, we can see that the nanoparticle actually wraps the RNA and actually creates this pretty symmetrical or regular structure. On the other hand, if we deprotonate this structure and we have the uncharged form of the ionizable lipid, we get the spherical form which we saw previously. And also the RNA actually doesn't stay inside of the lipids. A lipid nanoparticle and is released outside or leaves the structure. So I would like to point out that these channels, they are not empty. So there is also water and I think some ions as well. So the RNA is not only fully enveloped by lipids. There is a thin water channel around it. Which brings me to the final topic I wanted to touch in this talk about lipid phases and how the wide complexity of lipid shapes and charges and all of that can happen in real life, and how it actually creates all these various forms. So these are, by the way, one of the most recent pictures of the inner structure of lipid nanoparticle. So the resolution here is slightly better than it was a couple of years ago, but it's not. We're still not there. We're still not completely certain what is going on inside. And one thing about hexagonal phase is that by definition, you have the channels. They are ordered in this hexagonal shape, and also there is this like tiny triangle inside, which is it cannot be empty, right? Nature abhors vacuum, so there has to be something that fills it so that the lipids are in like energetically favorable state. And one thing that has been discussed recently is that inside that that the lipid nanoparticle is not actually homogeneous in its structure, but that there are different layers that can have like different microenvironments if you go from the inside from the outside. And of course, the protonation state of the lipids is not, there's not like 1 or 0 in nature, so there is a continuum of different protonation state that the ratio changes based on the pH and pKa. So I would like to leave you with our current project, where we are trying to explore this further. And I love this snapshot because it shows basically everything I've talked about in this talk. So we have ionizable lipids in the charged form, in the red form, that are on the outside. They are curved, they are disordered. They create these stalks. And they have like this one curved surface on the outside. They have one curved inside surface on the inside of this water channel with RNA. So actually, these spheres of the hexagon are not, the same size. We can see cholesterol that actually creates this patch that is almost a bilayer. It's almost lamellar. There is some separation of cholesterol and helper lipids as well. And we can also see that the ionizable lipids in the uncharged form in the green, they actually fill, because they are more, the ionizable lipids in the uncharged form are actually more hydrophobic. So because they don't have the charge on the nitrogen, so they actually localize inside of the structure and fill all of these spaces between, the curvature, so that the whole system is energetically, favorable state. And actually, it is actually similar to what we saw in the previous study with the BOPE and, the ionizable lipid deprotonated that creates this like droplet inside of the bilayer. With that, I would like to just summarize what I've said here. And basically that lipids are biological molecules that have a great variability of structure and function, and cells use this variability to put them into membranes that actually have a wide variety of properties inside the cell. Lipids, because of this variability, they can make different shapes and forms, and like this very complex multi-dimensional assemblies. And we as humans took advantage of that and engineered lipids that actually can be used to deliver pharmaceutical cargo, medical compounds. And with that, I would like to thank to my colleagues, Markéta, Martin, Petra, and Michal. I would like to thank our funders, notably the Project TechScale that pays my salary, and Ministry of Education that that provided that with this project. I would like to thank the Cost Action for bringing us all together and making this event possible. And I would like to thank you all for your attention.
Thank you very much, Petra, and let's thank Petra for this very important. And now we have time for questions. Please raise your hands in our room, in Zoom. So probably our participants are thinking about questions, and I would like to ask a question. Maybe, yes, I see Vlada Anatolievna, and I give you, but I would like to ask maybe some general question. I see that there are so many things already done with phospholipids and with membranes. It's extremely interesting, actually, this review of all these methods that can be used to model the systems and to create the system. And actually, I'm wondering if it's possible to create such software that in the input you can provide some information about structures that you would like to have, and the result you obtain as an output some structure of the phospholipid with length of tail and something like this, and conditions of environment like pH and ions to obtain some structure as you show at the end. So this beautiful picture with packing with some sort of these particles, phospholipid particles. So maybe this is the complex problem in general, but probably it is possible to create such a software because you have so many information already.
Yeah, so actually, this is the topic of our perspective in the COSI special issue. So it is possible. I mean, so the problem is that currently each step of the process. Okay, let me go back to the presentation and just find the relevant slide. Okay. So basically, the thing is that we have these different parts of the system, right? We have lipids, we have solvent, we have everything else we want to put there. And actually, there are different tools for different steps. So you have one step that is the parameterization of the components of the system. Then you have a different software that actually puts it together. And then you have another software that actually runs the simulation, and then you need to evaluate it by yourself. So that is something that it's and especially if you want more complex systems, 3D structures, it's really, really hard because bilayers are 2D structures, and when you do something that is there is some local environment, you do it on the grid. That's the easiest way how to do that, right? You just cut it into bins and then calculate a local property in the bin. But if you move to the 3D, to more complex systems, the grid actually increases, in the third dimension, right? So it's suddenly the problem becomes computationally very, very hard and very, very demanding. And we actually hypothesize, in this perspective, we mentioned some ways how it could be and possibly might be solved, even with AI advanced protocols programming on something. But for now, it really is an open question, and
yeah. I just asked him because it looks like smart materials, so you can control some properties of the system.
Yeah, I mean, actually, some of the algorithms are inspired by materials and material science, but still there is this barrier between people who do simulations and people who of biological systems, people who do simulation of materials, and people who program the algorithms. So I guess this is the biggest barrier to have streamlined process.
Thank you, Petra. Very, very, very interesting. And now we have a question from Professor Koshinska.
Thank you very much, Petra, for absolutely great lecture, for final lecture of this day, because it's very interesting for our department, Molecular Biophysics Department of the Low Temperature Physics and Engineering Institute in Kharkiv, because we are study for drug delivery problem, related to drug delivery problem, nanoparticles, also lipid nanoparticles and non-organic nanoparticles, molybdenum disulfide and so on, and try to characterize by physical methods. And surely this problem of RNA-based vaccine, it's very interesting for us. Also taking into account that everybody of us were vaccinated by COVID vaccine. And for me, it's very interesting now the problem of controlled release mRNA or drugs from such nanoparticles, for example, lipid nanoparticles. I know from literature that it's a pH-controlled process. Did you calculate or did you model or are you modeling the process processes of controlled release your RNA or other biomolecules from such nanoparticles which you constructed by modeling? Thank you.
So one thing we try to do is actually like change the pK, the pH, like 0 to 1. So we either have like all ionizable lipid charged or ionizable lipid uncharged. There are groups that actually run what it's called constant pH situation, when they can actually have gradient of the numbers of charged and uncharged molecules. And we try to mimic that by actually manually putting ratio, different ratio of charged and uncharged molecules in the most recent study. It is, we are making steps toward modeling that. It's not a simple process, because the way we treat the ionizable and protonated and deprotonated ionizable lipids in these studies is they have different parameters, right, for the molecular dynamics. So it's not easy to like just to switch one to another. At least in atom, it can be done in coarse grain more easily. So
and have you seen the release RNA from inside of these nanoparticles, or destroying nanoparticles, if you change it conditions like you mentioned?
Yes. So we can see that the RNA is released if the system is deprotonated.
Excellent.
And we can see that water is actually leaves the center of the nanoparticle as well.
Thank you very much. It will be interesting to see. Thank you. Great.
Thank you very much. And now we have a question in chat. Can molecular dynamics simulations be used to investigate how lipid geometry and packing parameters affect the long-term stability and shelf life of lipid nanoparticles based on drug formulation through nanodroplets? So that is to characterize stability through formation of nanodroplets.
Yeah. Okay. Let me. I'm not sure if.
Yes,
if
you can read. You can read too.
Yeah. Sorry. I will just go back to sharing my screen, and if I just go a little bit back, I'm not. Yeah. Okay. This is the slide I want. So one thing. So we cannot like see it directly, but we can provide some explanation mechanistically. So if you, I will go. So this is the lipid that is used in the Pfizer formulation of lipid nanoparticles, right? You can see it has 4 tiny tails, or 2 tails, and that kind of are divided to 4. And in the case of Moderna, the Moderna ionizable lipid is actually this lipid 5. And you can see that one of the tails is also branched in this similar way to 2 small tails, but the other tail is like straighter, and it isn't branching. And we actually did some simulation with the Moderna lipid as well. And what we could see in our simulations, that the Moderna lipid did basically the same thing as the Pfizer lipid, but more slowly. Like the dynamics was more slower. The system was slightly more ordered, and it actually, for us, it actually corresponds pretty well with the storage requirement of the lipids, of the nanoparticles, because the Moderna lipid, which is like more ordered, more or less dynamic, needed to be stored in like freezer, right? Normal temperature, I think -20 or something like that. Whereas the Pfizer lipid, which is more branched, more disordered, and kind of more flexible, needed to be stored in the -80. So we cannot see it directly. I mean, if we have like large enough data sets, I think like machine learning amount of data, that which probably would need it to be different, like very specific sort of simulations. There might be some correlation or some predictions, but we cannot like make it directly yet. But we also can like see some mechanistic understanding of the shell stability that we already have the real data for. Does that answer your question?
Yes, I suppose yes. And now, yes, we have another one question, please, Alexander Chernev.
Thank you for a very fascinating report. I'd like to ask about, well, my apology in advance if it's incorrect, but have you studied some auto oscillations of this membrane in shape or maybe in this like ionizations of the surface and well, can such processes be dealt by this molecular dynamics in like I think like seconds, or that's just impossible.
Sorry, I couldn't quite hear the question.
Let me try again. You described that in particular in some slides that there is some ionization can be at the surface of the membrane due to some processes. I'm not sure I remember what these processes are. And my question is, if you have a membrane and you have you observed any auto oscillations like the string if it
Microphone close.
okay. If it I'm sorry. It's okay.
No problem.
Fixed.
If it's fixed in advance. So do you have some auto oscillations of ionization or of the shape of the membrane?
So there are some membranes that actually are more heterogeneous in their structure, but and there are some membranes that actually can be curved in the simulation. So if you have like large enough patch, there can be some like local properties. There can be curvature. There can be some like undulations of the membranes. But it's something you actually like have to allow for in the simulation. So the membrane has to be large enough and diverse enough in the lipid composition that, or you have like some specific lipids that tend to be curved that allow for the undulation of the membrane.
Okay, thank you. And well, if I'd like to simulate, if I'd like to simulate this kind of oscillations or change in shape for seconds using some software you have used, am I possible to do that or I'm not?
I guess it depends on what you want to see, because if you pre-assemble the bilayer into like a bilayer form, it's very, very stable. So there are ways how to like move a simulation to different, local minima. There was a talk about biased MD methods yesterday, so that's one way how to do that. You can change the temperature, so if you heat up the membrane a little bit, that it's more flexible. But to see any like larger scale, or like if you want to see like a specific like local environment, you have to have the membrane so large it actually can have the local environments, right? Because the membrane is connected, or any simulation box is connected through the periodic boundary conditions. So actually you need the membrane to be large enough to have some micro environments or stuff inside even before it reaches the periodic boundary. So it's doable in theory, but it's not straightforward.
Thank you.
So, thank you, Petra. As I understood, Alexander Chernak asked about the dynamics of membrane in the millisecond time scale.
Mhm.
So, and I think it should be used some coarse-grained models maybe, because on atomistic level, it's very large times.
Yeah. Yeah. So especially if you want to like see more complex mixtures, then coarse grain is more suitable for that.
Right. So this is large system.
Yeah.
Okay.
I mean, it's possible in all atom, but it depends on like what you want to see, and I mean, coarse grain might be just better.
Okay, Petra, thank you very much. Very interesting lecture. A lot of questions. Let's thank Petra once again.